All right. So we're taking derivatives here. So remember when we have sums and differences of things, we just essentially take the derivative of each piece and add or subtract them together depending on what we started with. So the derivative of 5 times t to the third, bring the power down, subtract 1 from the power. Derivative of 16t is just 16. Remember, that's kind of a power rule if you want to think about it like that, where you would bring the power down and subtract 1 from the power, but then you would get t to the 0, which is just 1. Or we kind of presented it as its own kind of separate rule at the very beginning. But, oh, okay, erase. And then we need the derivative of 2. There's no t attached to it, it's just a constant, so its derivative is 0. Plus the derivative of 2 times natural log squared. 2 comes along for the ride. Derivative of natural log of t is 1 over t. So if we want to clean this up a little bit, 15t plus 16 minus, plus 2 over t. Yeah, I don't know why I wrote a 2 in the, I wrote a 2 up here, which threw me off. Sorry about that. Thank you. So I screwed that up. I accidentally wrote a 2 instead of a 3, so it should be t squared, not just 2. Yes, this is pretty much what's on the quiz, is I just give you a equation. So the next one, kind of like last time, I'm just going to kind of chug along and take slight pauses after them. 1/2 comes along for the ride. Derivative of natural log of t is 1 over t. Subtract the derivative of e to the 0.5, so that's an e to the kt situation. So we bring the k out, but then we essentially, so I literally wrote k. So we bring that k value out and then essentially rewrite the entire thing. Plus the derivative of 20, there's no t attached to that, it's just a constant, so the derivative of a constant is 0. So I would personally write it like this, but as I've said a couple times, you don't have to simplify if you don't want to. Oh my god, plus 0, not 20. I'm off my game for some reason today. Yeah.
But when it comes to 20 and the derivative of that is 0, it's okay not to put that in the final answer.
Oh,
not part of it.
Yeah.
Okay.
Okay, so you know it's like 0.05 e to the 0.5t. Wouldn't you subtract 1 from like 0.5t?
So you're, I don't want to say confusing two rules necessarily, but you're kind of combining rules when you shouldn't be. So our rule for e to the kt is it's just k e to the kt. You're thinking of the power rule where we have to subtract 1. That doesn't come into play here. But that's been tripping up a couple people, so thanks for asking. So this would be final answer for that thing. Yeah.
So it's fine to keep it as like 1/2 times 1 over t.
Yeah. So essentially, either of these two lines, or the first line without the plus 0, as long as it's mathematically the same, I don't really care how you write it. And for this this last one, let me scroll back up a tiny bit so that last one can get in there. So the 3 comes along for the ride. Derivative of e to the kt, you bring the e out, the k out. What is wrong with me? And then essentially just rewrite the e to the kt. Derivative of 1/2 natural log of t is actually just what's done in the last one, but 1/2 comes along for the ride. Derivative of natural log of t is 1 over t. Plus the derivative of pi to the 7th, which is a number. There's no variable in that. So its constant is 0. Its derivative is 0. So I would write this as 6 e to the 2t plus 1 over 2t. But as long as it's mathematically equivalent, I don't care. Questions, concerns, but any of those? Yeah, what's up? Yeah.
Okay, so whenever there's like a number in front of, like for example, like the 3e to the power of 2t, you always multiply that at the end to the exponent that's brought out to the front?
Yes,
Okay.
as long as I'm understanding your question correctly, which I think I am. David?
Okay, for 6
Mhm.
plus what's it called over 7.
The pi to the 7th?
So wait, so you not have to do what's it called? Okay,
You want me to bring, do you want,
like you, okay, see how you do a switch to 7 on the first one? Then you subtract the 7 on the other thing.
is this what you want me to write?
Oh no, I was wondering if that's how it works, or either way. I got to make sure that one.
So this is kind of a trick that likes to be pulled a lot. Note that the variable we're working here is t, and there's no t in that at all.
Oh,
So it's just a number to a number. So since that is just a constant, just like 2 or 7 or -5, the derivative of a constant is 0. So we don't need to do that any of the other types of rules. It's just a constant. There's no variable there.
okay.
Okay.
The other thing you mentioned, pi, earlier, on the worksheet, that has to be included.
This so the pi was the variable, the pi was the power on the variable. So yeah, it definitely depends on that case it was attached to a variable, where in this case it wasn't. Only other nudge, nudge, wink, wink I can give you on your quiz is that you will want to remember your exponent rules for changing over a root or a 1 over something. Other classes didn't get that nudge, nudge, wink, wink, so you're welcome. Other than that, it's that similar ideas. We're just gonna give it a x to the 1 over n? Yeah. So like the 5th root of x would be x to the 1/5. That didn't show up. Or not. There it goes. Anyway, so yeah. Yes, so your quiz, I will give you a function. Just ask you to find the derivative. That's all you got to do. It does not include the chain rule or anything else that we will go forward with today. It's just these rules that we covered up to yesterday, excluding the chain rule, which we barely started. So, if there are no more questions, let's get going. Okay. How do I want to do this? Let me do this off to the side. Let me remind us what our chain rule looks like, because I have to scroll down past it. So since number 2 is so similar to number 1, I think I probably said I was going to go over number 1 again, but number 2 is so obnoxiously similar that I'm just going to go over number 2. So remember, with this chain rule, so let me scroll back up to the actual rule for a second. Oh, I want to do something else first. I'm sorry, I'm more scatterbrained than usual today. So remember, our chain rule is this weird one that kind of has all the other rules kind of lumped into it, because it just tells you how to deal with the composition, not necessarily what rule to use. So remember, we essentially have this inside function and the outside function. We take the derivative of the outside function, leaving the inside alone, and then take the derivative of the inside. A couple tips before we go on to some of these rest of the ones. Anyway, we can essentially rewrite the rules we've already talked about kind of in terms of chain rule. So let me write, so z here, whenever I write down a z in the things I'm about to write, I'm essentially saying it's equal to some type of function. So it's something that's more complicated than just a single variable, but just for the sake of our sanity, we're just going to write z. I also need to split this up a little bit. So kind of the 3 main rules we have seen already is either something to a power e to the something, and I'm not going to say k something, I'm just going to say something, because remember, way back when I said that was technically a chain rule, and it is. And we also have the natural log of something. You're going to hear me say something a lot. Something to a power, e to the something, natural log of something. Because essentially, so let me write this down first and then I'll finish the rules that I'm about to write out. So essentially, these are our three choices, like 95% of the time. Maybe less, maybe slightly less than 95, but these are kind of your choices for your outside function. And that's why I kind of phrase it in terms of something. Is it something to a power? Is it e to the something? Is it natural log of something? This is also up to a constant. So, you know, you could have 5 times e to the something or 2 times natural log of something. So if there's just a constant hanging out front, it doesn't really affect it at all. Because remember, that constants just kind of come along for the ride when they're multiplied to a function. So essentially, these rules are kind of going to stay the same, but now they're going to kind of have this last piece kind of tacked on the end. So, well, what was the derivative of something to a power? We brought the power down, and we subtracted 1 from the power. But essentially, what our chain rule now says is that we need to take the derivative of that thing. And if you want, you can think of this as like a g prime of x, because I've said that it's going to be equal to some function, if you prefer that type of notation. And what was our original e rule? Well, the derivative of e to the x was e to the x, so it would essentially stay the same, but now our chain rule says to take the derivative of whatever that thing was, whatever that power is on the e. And again, you can think about this as a g prime of x if you prefer that notation. And then lastly, well, what was our derivative of the natural log of x? It was 1 over x, so we're still going to start that way when we do these for the chain rule, but then the chain rule says to tack on the derivative of what is essentially whatever is inside that natural log. So it's not that we're not using these rules still. It's just kind of that the chain rule gives us this extra kind of end piece that we also need to include now. If the thing that's on the inside of that function is more complicated than just a singular x or a singular t or anything like that. So I'll wait a couple seconds for y'all to get that down really quick. Yes, Sydney, exactly. The z here is what's essentially representing the inside function for that chain rule. Exactly. Okay. So, yeah. I would say focus on the, so she asked how to figure out what the inside function is. I would actually suggest focusing on the outside more, and then the inside just kind of falls out. So let me scroll up. Like number 2, if I was trying to figure out which one of my three choices I'm in, am I something to a power, am I e to the something, or am I natural log of something? If I look at you, that's something to a power, right? So I would focus on finding that first. Now that gives you your outside function. So your outside function is essentially z to the 5th. Well, what's the z? That's the 3x cubed minus x. So I think it's easier to think about it outside first, and then the inside one just kind of falls right out. All right, so number 2. As I kind of already said to her, this outside function is essentially, something to a power. This is essentially some y equals something to the 5th. So if I want to take its derivative, the chain rule says I have to take the derivative of that outside function first. So if I have something to a power, I use my power rule first. So I bring the power down, I subtract 1 from the power, I'm going to stop writing the -1 piece. I'm just going to jump to the actual numerical answer. But we leave that inside piece alone. So like, if this is my derivative of my outside, that's kind of 5 in the 4 situation. And then I've got to leave the inside alone. Well, that's the inside left alone. And now the chain rule says take the derivative of the inside. Well, what was our inside? The inside was the 3x cubed minus x. It's lagging. Let me just unshare and reshare. That usually makes it stop being a dork wad. Here we go, more colors. So now I got to take the derivative of the inside. So it's the derivative of 3x cubed. The 3 comes along for the ride. You bring the power down. The 3 times the 3 that you bring down will give you a 9. X squared. Minus the derivative of x, which is just 1. Once it catches up to me. There we go. Now again, well, actually, I don't remember if I told this to your class or one of my other classes, but anyway, one other thing I sometimes note, because sometimes people don't know when to stop doing the chain rule, and they just keep taking derivatives and derivatives and derivatives and derivatives, and then it's just no, you gotta stop eventually. So one thing I can suggest, if it helps you, go ahead and, if you don't like it, forget it. But say I was trying to take the derivative of this. Well, I see that my outside function is something to the 5th, so I do the power rule. Once I do the power rule, I essentially don't care about that 5th power anymore, and I just have to take the derivative of what's left. Well, what was left? Well, I had a 3x squared, so I took the derivative of that, and then I took the derivative of the negative x. I don't have anything else to take the derivative of, I'm done. That comes in a tiny bit more handy when we start having chain rules inside of chain rules inside of chain rules. No one can see my awkward smile. This is killing me anyway, but anyway, so if kind of crossing it out along the way helps you keep track of what rules did you already take care of, go ahead and do so, because you do eventually stop. And sometimes people have a hard time figuring out when to stop. Anyway. If you wanted to, you could, distribute that 5 through here. Totally unnecessary, but if you wanted to, you totally could. Just in case. I probably would have left it like this because I'm lazy. But number 3, we've got ultimately, out of our kind of 3 options for our outside function, we have natural log of something. So we got to kind of do that rule. So what's the natural, my words? What's the derivative of the natural log of something? It's essentially 1 over that something. So we start with 1 over q squared plus 1, which essentially takes care of that outside natural log piece. So then I have to take the derivative of the inside of that q squared plus 1. Also, that derivative of the inside gets multiplied at the end. There's like multiple pieces to these. The other thing I see a lot of people doing is they'll take the derivative of the inside, but they'll like put it inside of the other rule. Like they'll put the derivative of the inside down here, which is not good. So it's kind of like multiple steps. Take the derivative of the outside, leave everything else alone. So if it's the natural log of something, it should turn into 1 over that something times its derivative. Anyway, so what's the derivative of q squared? It's 2q. What's the derivative of 1? It's 0. So of course you don't have to write that if you don't want to. So I would personally just clean it up a little bit, but as I said before, whatever floats your boat, you don't have to really clean them up if you don't want to. Yeah.
If we just left it as like 1 over q squared plus 1 times q, is that okay?
My brain freaked out a little bit when you said that. That's fine. For some reason, my brain registered the +1 in the wrong spot, and I was panicking a little bit. So let's go up to 4. Savannah, no. So, well, Triple check my instructions, see if I ask you to simplify, but I usually don't. So on the quiz today, I specifically said, well, I forget what it's like on Blackboard, but the ones on paper, I specifically said, you do not need to simplify. If the instructions don't say specifically simplify, then you're fine. And I will tell you, I don't think I've ever required simplification on these. So no, you wouldn't get points off if you didn't simplify. All right, number 4, we've got a sum of things here. So now we have to bring in that sum rule again. So essentially it means that we need to take the derivative of this and then the derivative of the 17 separately. Let me zoom in a little bit. You know what? I should just do that when I need to move because that's just so much simpler than me fumbling around. Anyway, but that e to the negative x squared is a chain rule because that thing in the power is more complicated than just a singular variable x or a kx in our case. So if I want to take the derivative here, out of our 3 choices for our outside function, we're in an e to the something case. What's the derivative of e to the something? It's e to that something. We've taken care of the e rule. We now have to take the derivative of the inside, which was the negative x squared. That gets multiplied to the back. Well, doesn't it? Nope, never mind. What's the derivative of negative x? Bring the power down, subtract 1 from the power, you get negative 2x. Taking care of the negative 2x, sorry, the negative x squared. We've got nothing else to take the derivative of for that chain rule. So now I just have to add on the derivative of 17. 17 is just a number by itself. There's no x there, so the derivative is 0. Personal preference, I like to put everything that's not attached to the e in the front, but again, you're whatever. Let me clean that up a little bit. Questions, concerns? For the sake of moving forward a little bit, mainly for your homework's sake, I'm going to move on to the next rule. We'll come back to these eventually. I don't know if it'll be today. It'll probably be Monday. So we'll hit everything we miss on Monday. But just so that you have more stuff to be able to do the homework, I want to move on to the next rule. This really isn't really part of it. Probably won't get back to it till Monday, but Tuesday, whatever, you know what I mean. So our last 2 rules are called the product and the quotient rule. Now they're like the tiniest bit similar to chain rule in that, the other rules kind of work inside them, but it's slightly nicer than chain rule because it follows a bit more of a process. So let me break this up so that I don't run out of space. So if I want to take the derivative of 2 functions that are multiplied together. Now I can't write it straight across because I'll run out of space, so I'm going to jump down here. And just like with the chain rule, I'm going to jump between the 2 types of notation. So now I'm going to use Newtonian. What you do is you take the derivative of the first function and multiply it by just the regular old second function. Then you leave the first function alone and multiply it by the derivative of the second function. I personally memorize this as f prime g plus fg prime and just forget about all the of x's because those are tedious. So besides writing it out formally here, I will always write f prime g plus fg prime. Let me write the quotient rule and then I'll say some things. Quotient rules for when we have 2 functions that are divided by each other. Well, one divided by the other. Take the derivative of the first, leave yourself some space on the bottom, times the regular old second, minus the original first, times the derivative of the second, all divided by the original second function all squared. Maybe I should stop saying seconds because it's more top and bottom in this case. Some people will say that as low d high minus high d low all over the square of what's below. I didn't learn that until college, and I took, no wait, yeah, no, it was college. Calculus 3. Someone finally said that to me, and I was like, excuse me? What is that? Because I just memorized it as f prime g minus fg prime all over g squared. So I just use f's and g's and forget about the of x's because those are tedious. Now notice, they are similar in a way. They both have f prime g and then fg prime. Product rule has a plus, quotient rule has a minus, and then of course quotient rule has the extra divided by g squared. Technically, and I'm almost scared to say this, the order in product rule doesn't quite matter. So say you wanted to do g times f prime and then g prime times f, or you wanted to do fg prime plus f prime g and kind of switch things around, as long as you kept the two things that are supposed to be grouped together. So a lot of people will present the, I had to think about it because I've never written it like that before in my life. We'll present the product rule like that. I suggest just memorizing it in this order because, again, it kind of links to the order of the quotient rule then. So it's kind of like you don't have to remember two different orders. But anyway, so this is kind of how those go. So we'll do a couple of these. Oof, it'll be all right. So again, these ones are kind of nice because they have that kind of set order, if you will. So what I like to do, this isn't like you don't have to do this, but what I like to do for these is I like to kind of come off to the side and do a little chart. All I did was draw a straight line, but not up there yet. So I want to look at number 1. Now, number 1 is kind of just for illustration purposes because you could technically make that x cubed and then just do a power rule. But just to kind of show you that this does come out to be what we kind of want it to be. What I like to do is I like to kind of pop over to the side and write down what my f and g are and then find f prime and g prime and then just stick it in the right order. So what's my f? My f would be my x, and then my g would be my x squared. What's the derivative of x? It's 1. What's the derivative of x squared? It's 2x. And then you can kind of just shove them together in kind of a crisscross order. And then add their products. So f prime g would be, if I write it out in full generality, we would have 1 times x squared plus x times 2x. Again, in general, you could stop. But let's just keep going a little bit in this one. So we would have x squared plus 2x squared, which would be 3x squared, which is what we would expect. Because if you think about this, the original was equal to x cubed. And if we just did a power rule on that, we would have gotten 3x squared. So if you don't trust to believe that the product rule works, it works. Yeah. Oh, in this situation? I doubt I would give you one like that, but if I didn't specify, you would get to choose. I don't really do that, but I really just threw this one in so that, because some people want to say, oh, well, the derivative of x times x squared is just the derivative of x times the derivative of x squared. No. We got this fancy thing we got to do. So it's more for like illustrative purposes. I don't think I'd ever really throw that at you and make you choose. But anyway, zoom in a little bit. Oh, Lord. Let me scroll down here. I'm going to do 2 and 6, and then I'm going to jump to something else again for the sake of your homework. And again, just hit everything that we didn't get to on Tuesday. You know what I mean. So, excuse you. Here, if I come off to the side, again, you don't have to do this little chart. if you can just kind of see what's going on. But especially once they start getting more complicated, I think it's kind of nice. So what's my f here? What's the first thing that's being multiplied? It's x squared, and then we have e to the 2x. Also, well, no, a lot of people don't usually get freaked out by that. But if you get freaked out by the fact that the function's named f, and I'm also talking about f back here, you can totally make those letters whatever you want. If you want it to be a and b, or whatever floats your boat, go right ahead. But anyway, so what's the derivative of x squared? It's 2x. What's the derivative of e to the 2x? Well, here's a nice place for me to say, see exactly why the e to the kx rule is actually a chain rule. Let me do that in a chain rule fashion. That's an e to the something. So the derivative of e to the something is e to the something. Then I have to take the derivative of the something, which was 2x. What's the derivative of 2x? It's 2. So that's why that e to the kx rule is technically a chain rule. So don't think you have to use a chain rule on an e to the kx. It's just, it is, Sydney, but way back when we wrote down that rule, I wrote that it was technically a chain rule. So since it's technically a chain rule, I just wanted to go through the full chain rule process on that to show you that I meant it. No, you can still use this e to the kx rule. That's perfectly fine. I just wanted to write it. I just wanted to talk about it in terms of a chain rule so that we recognize that it technically is. But you can just write 2e to the 2x and be perfectly fine, Sydney. No, that's perfectly fine. So what's the full derivative here? F prime times g. So I wrote out what they actually were as I said them. Plus the f times, now I'm going to put that 2 in the front now, just personal preferences. If you kept it at the back, that would be perfectly fine. You could totally stop here. Personal preference, I like all of my constants in the front of the term and all of the e stuff at the back of the term, but that's just personal preference. You could totally stop here and it would be fine once it stars. Start, there we go. Questions, concerns so far? Okay, let's do a quotient rule then. So let's jump over to number 6. And again, everything we've skipped, we'll come back to later. Same idea. If you want, you can pull out like a little chart of what's your f prime, what's your g prime. And in this case, sometimes I'll forget to write down the g squared because I just bring it in at the end. But if you want to write that down as part of your chart, that's perfectly fine. So we've got 5q squared as our f and our q cubed plus 1 as our g. What's the derivative of 5q squared? It's 10q. Bring the power down, subtract 1 from the power, but the 5 times the 2 that you bring down gives you 10. What's the derivative of q cubed plus 1? 3q squared plus 0. For your g squared, unless it's something super simple like just an x or just an x squared, just tack a squared on it and call it a day. So I'll do a little side note up here, not really a side note, but just reminding us of what the rule looks like. We've got f prime g minus fg prime all over g squared. So our f prime is 10q times g. If your thing has more than one term in it, if it's got addition or subtraction, put it in parentheses, please and thank you, once it catches up to me. So that's my f prime times g minus f times g prime. You can also just put everything in parentheses if that makes you feel better. And then q cubed plus 1 all squared. We could, of course, simplify that down a little bit, but I've also run out of space, so I'll just stop. Yeah. Yes. I was gonna do that up here in number 5 that I've skipped. And I'll talk about that on Tuesday. But essentially, there's a way, and I'll show you on Tuesday, that you can make every single quotient rule into a product rule. But just know that that also makes it a product rule that includes a chain rule. So sometimes people don't like to do that. I've known a couple people who refuse to use quotient rule. My fiance is one of them. I don't get it. Just use quotient rule. It's easier. I don't understand it, but whatever floats your boat. So I'll show you guys that on Tuesday. Questions, concerns on that setup for that quotient rule? Yeah.
For like simplifying it, like, would you just multiply 10p by q3 and multiply that to
If I were being the lazy self that I am, this is the main thing I would have done, is to squish the back thing into a 15q to the 4th.
so if like
It-
we want to get from up like that as 10p.
No. If I was not going to be the lazy butt that I am, then yeah, I would probably push through that 10q and multiply it by the q cubed and plus 1. But I'm lazy. So
And that's the same thing with the -5q times 3q squared.
if it triple check my instructions, but again, I rarely ever specifically ask you to simplify. And honestly, it's easier to grade if you don't. So if I'm being the lazy person that I am, I almost don't want you to simplify. Oh, no. So Kira, that's actually something that, that's a good question though. It's not the second derivative, or it's just g squared, and that's because in our rule, we have to take that denominator thing and square it at the end. So not the second derivative, it's just me squaring the denominator. So I took the original denominator and I just square it. And that extra piece comes in because we're doing a quotient rule instead of a product rule. So quotient rule has this kind of tiny extra piece of that g squared on the. Hopefully that made sense. Yeah. Again, I'm sorry for skipping around a little bit, but I want to jump down to something else because of the fact that it comes up on your homework, and if people want to get it done before Tuesday, I want you to be able to do so. And it's ones that look like this. My favorite, nudge, nudge, wink, wink. Everyone else hates them, but I love them. So what happens with these is we don't have like an actual equation. We're just given a generic format, and we're asked to find a derivative, and we're given a couple values. This can also, I'll get to that in a second. I'm running out of time. Woo. So first it's asking me for h prime of 1, where we're told that h of x is f of g of x. So we're told up here what h of x is. And we're given a bunch of these values that we're going to have to potentially use. Maybe not all of them, but probably at least some of them. So this is actually where it's going to be highly important for you to know those rules, chain rule, and this comes in a lot for product and quotient rule as well, and you need to know them generically. So the first thing I would have to do is I would have to find the derivative of this function h, but it's just the generic format. Well, what's the chain rule tell me? It tells me that I have to take the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. Now, in this case, it was nice because it essentially follows, that's exactly what the chain rule looks like. But be careful in case, like the other one was g of f of x, so it would kind of be flip-flopped. So if I want to evaluate what h prime of 1 is, well, that would mean that I would have to put a 1 everywhere I see an x. Now I can start figuring out what this is. Remember, when you have a composition you want to work with, which is this first term, always start inside out. So the first thing we need to talk about is this G of 1. What's G of 1? It's 0. So that would become F prime of 0 times G prime of 1. What's F prime of 0? It's coincidentally also 0. What's G prime of 1? It's 1. So we'd have 0 times 1 is 0. That makes sense? If I really quickly want to do the other one, so now we want K prime of 1, where we're told that K of X is G of F of X. And now I'll scroll down because that was up here. But now that I've written it down, I don't need it anymore. What is K prime of X? Now this is where it gets the tiniest bit trickier because now it doesn't follow 100% exactly the chain rule because the letters are now kind of in the opposite order, if you will. So our chain rule says derivative of the outside, which in this case is G prime, leave the inside, which in this case is the F of X, times the derivative of the inside. Plug in 1 everywhere you see an X. New color. Inside out for composition, so you want F prime of 1, sorry, F of 1 first, which is coincidentally 1. And then I already used G prime of 1, so I can reuse that color. Woohoo! Orange. And then F prime of 1 is 3. One times 3 is 3. I love these types of problems. Nudge, nudge, wink, wink. I love them a lot. They're so fun. Okay. One more thing. I know I'm starting to, we went over a lot of the heavy stuff today, so I know your brains are probably a little fried. We can do a similar thing to this idea, but instead of just being given the straight values, now I gotta find the one I want to look at. This one, but I'm just gonna look at 3 and 4 because we're running out of time. And again, we'll hit everything we didn't hit on Tuesday. But I could give you a graph. Crap. Forgot that those graphs aren't labeled. I think, well, I guess it doesn't matter. I can just pick which one I want to be which, and it doesn't really matter. I think this one's supposed to be F of X, and this one's supposed to be G of X, but we'll just, they are now, so there we go. So 1 and 2 for this would be similar to what we just did, just with this different graph idea, which we'll talk about in a second. So I want to focus on 3 and 4. Maybe we won't get to 4, but at least focus on 3. So essentially, if I wanted to find the derivative of that thing evaluated at 2, now I don't have a lot of space for this. So what I'll do is I'll write the derivative and I'll put in 2 at the same time. Well, what does the product rule tells me? It tells me F prime G, so I would need F prime of 2 times G of 2 plus F of 2 times G prime of 2. So I did kind of do 2 steps there, but it was just writing the generic derivative and then just replacing 2 everywhere I saw an X. Now, notice we've got kind of original function things, and we've got derivative things we want to plug in. So given this graph, well, we're given regular f and regular g. So if we just want f of 2 and g of 2, just look at 2 and find where they are on the function. So we've got y equals 4 for f of x, so f of 2 would be 4. Why did that was supposed to be a parenthesis, but it got a little rogue there. And then where is g of x? G of x is at 6, so g of 2 would be 6. So I'd have 6 and 4 so far. Well, what about my derivative pieces? Remember, the derivative is a slope. I'm getting a little loopy. So derivative is slope. The nice thing is I've got straight lines here. So the straight lines, finding a slope of a straight line is very nice. So the same thing, though, is we're looking, what is the slope? What is the slope of these points at 2? So we're essentially looking at the slopes at those 2 points. But since they're on this entire line, we just find the slope of that line segment and that point is on. So what about if I focus on f prime of 2 first? So let me find the slope of this line. So essentially, if I look at this, I would go over 2, because this is, make sure you keep track of the units. So I jump over 2 and I jump up 1, 2, 3, 4. So that means the slope at 2 would be 4 over 2, so 2. So that means f prime of 2 would be equal to 2. And then what about the function g? I jump over 2, sorry. And then go down 1, 2, so I went down 2. So g prime of 2 would be negative 2 over 2, so negative 1. I ran out of space, so I have to go backwards. 2 times 6 is 12. 12 minus 4 is 8. I'll get there. So I do want to stress, though, the last two that we just did, the last two types that we just did, are the same idea as just using those rules. We just no longer have that actual equation we're working with, but it's still that same idea of using the rule. I just wanted to show this to you because I know there are a few on your homework that are similar to those. I think your homework is made up of ones that look like that, and then I think most of the rest of them are just literally like find the derivative, plug in a value. Because again, remember your homework this week is kind of in 2 parts. You got the official stuff on Wiley, but Wiley absolutely sucks for the just generic find the derivative stuff. So you have that extra practice that's, you know, kind of optional, but highly suggested to do at least part of it. That's up on Blackboard. But the stuff on Wiley, if you're confused as to why it doesn't look like the stuff we did, you know, up here, you know what I'm trying to say. The stuff up here, it doesn't look like that because Wiley literally doesn't accept correct answers. Literally. And I didn't want to field 5 million bajillion emails in one day. Wasn't doing that again. Anyway. Any more questions, concerns about any of that really quick? We're actually perfectly on time for our quiz, so it's not like I used up too much of our time or anything, which is good. Last minute nudge, nudge, wink, wink. Remember your exponent rules that it hasn't scrolled down enough to show you. Oh, whatever. Remember your exponent rules that you can kind of see right here, but I've scrolled down, it just hasn't registered it yet. All right, let me stop the recording. Let me